Thank you for the introduction. Thank you all for being here. And thank you to all the AstroTours organizers. Today, I will be speaking to you about what our sun can teach us about the plasma-filled universe. So I wanted to start off with sort of a historical outlook. Since the dawn of human history, we've been extremely fascinated with the sun. If you think about it, there's this giant glowing orb in the sky. We quickly realized we needed it for survival, so it makes sense that people were curious. So on this slide, I have some art, and there are so many art pieces, but these are just a few. On the top left, some art from ancient Egypt, where you see sun worship. On the bottom left, some art representing the Hindu god, which represents the sun. On the bottom right, some art from the 5th BC, I think, of the Greek god Helios, which represents the sun. And on the top right, something that I thought was very interesting is the Nebra sky disk, which is basically the first recorded art piece of any celestial object or the sun in general, and it dates back to 1600 BC. So that's thousands of years ago. So basically, every single culture was studying the sun or thinking about the sun or making stories about the sun. The ancient Babylonians tracked eclipses, and the ancient Chinese used to track sunspots for their calendars. And this sort of led into the Renaissance era, where scientists that you may have heard of, such as Copernicus and Galileo, were studying the sun in a lot more detail. So Copernicus was the first to sort of suggest that we all orbit the sun and it's not the other way around. And Galileo, who did many things, also was tracking the sun and studying these features that he sees on the sun. So yeah, we've been looking at the sun for a long time. So in the modern day, you may know that we have sophisticated instruments that study the sun. On the top left, I have a GIF of a NASA instrument that studies the sun. You may associate the sun in your day-to-day life with a beautiful day, which we aren't getting many of in Toronto, but they happen. You may associate it with the reaction of photosynthesis that plants have to do in order for them to live, but also for us to live. You may also think of the sun as a hazard, and you might protect your eyes and your skin from it. If you're a kid, you might start every single drawing with the sun in the top corner of your page. So these are all just showing the presence of the sun in our day-to-day lives. You know about it, we see it. But interestingly enough, there are still a lot of things that we don't know. So I'll be touching on that a little bit today. So let's start with things we do know. So our sun is basically a giant ball of hot plasma, and I will talk about what a plasma is for a lot of the talk, so don't you worry. It formed 4.6 billion years ago, and its mass is roughly 3/4 hydrogen and 1/4 helium. There's also trace amounts of other elements in there, but it's very small. And now that we have cataloged other stars, looked at a bunch of other stars in our galaxy and beyond, we know that it is a very typical star. So it's pretty run-of-the-mill, average size, average brightness. So yeah, so nothing crazy. So I'll give you an overview of the talk today. I'll start off with basically talking about what a plasma is, where do they exist, and then the bulk of the talk will be talking about solar physics, or the physics of the sun. And then I'll transition into some concepts about plasma physics and talk about sort of the connections that they have with astrophysics and the implications of all of that. And then lastly, I'll end off with some tools that we use to study plasmas. So hopefully that sounds good and we can get started. Okay, so let's begin with what a plasma is. So it's often referred to as the fourth state of matter. So after solid, liquid, and gas. It is most similar to a gas, but it is ionized. And what ionized means is that there is enough energy in the gas to basically rip apart the electrons from their atoms. So you're left with sort of the soup of these electrons and these nuclei that have now lost their electrons. So because of this, they're now charged particles. And what charged particles do is they conduct electricity. So plasmas exist in many different contexts. They can be made artificially. Oh, I have a laser pointer. They can be made artificially, like in neon signs. And my my hands are so shaky, and plasma globes, which you've probably seen in a museum. And basically, these are made by heating a gas to a very high temperature. They also occur terrestrially, so like in a fire or in lightning. And they, of course, occur astrophysically. So in stars, in our sun, and in our sun is a star, in our sun, and then also in other astrophysical objects, such as around a black hole, and in other types of very extreme stars. So yeah, that's all I have to say. Okay. So basically, as I was making these slides, I learned a lot about the history of a lot of the concepts that I'll be introducing. So I'm going to throw that in there a little bit. And basically, the concept of a plasma sort of came about from the evolution of three very distinct and independent fields. So the first field is of electrical discharges. And what this means is basically what happens when we heat a gas up. So this is sort of a picture of that. So this is Langmuir here, who basically did experiments of this, and he's the one who came up with the term plasma. Then the other field is the people who are working on the sun and understanding the sun and our environment, or the solar environment. And then lastly, there are people who are working on kinetic theory, which is basically the theory of what happens when our particles collide, when they interact. Yeah, so that's basically where it started. And we now know that there are various scales of plasmas. So in this plot here, I'm basically showing you the temperature on the x-axis and the density of electrons. And what that means is basically in a small space, how many electrons do I have? So if you look at the very extreme case over here, when you have a very hot and very dense plasma, you'll have something that's like the center of the sun. So it's very hot, very dense. But then on the other side of the extreme case is when you have a very low temperature and low energy density or electron density plasma, then it's sort of like the interstellar medium, which is basically the space that exists between stars. So there are three distinct areas of plasma physics research, I would say. In industry here on Earth, in the sun and around the sun, and astrophysical plasmas. So today I'll mostly be talking about the sun, but I will definitely touch on the other ones as well. Speaking of which, we'll start off with applications of plasmas in industry and in the lab. So basically, again, we make a plasma by heating a gas to a very high temperature, and they're used in many different areas of research, industry, technology. I have some examples here. So you can use a plasma to cut metal. We have plasmas in our fluorescent lights, and plasma is also used in the area of combustion research. So in this plot, what I'm basically showing is that when there's no plasma, your flame sort of dies out by the end. But if you do have plasma in your combustion system, it can sustain the flame for longer. So yeah, many different applications. I can't list them all, nor do I know about them all, but yeah, very interesting. So another very important application of plasma physics is in nuclear fusion. So nuclear fusion is basically the reaction that happens when two light atomic nuclei combine to form a heavier one. And what happens is this releases a lot of energy in the process. So here you basically have your two light atomic nuclei. These are basically just versions of hydrogen, but they have like different numbers of neutrons in them. And then they combine, release helium, a neutron, and a bunch of energy. So nuclear fusion basically as a research area evolved after we found out, or the scientist Eddington basically suggested that stars undergo fusion, and that's how they sustain themselves. So after we found that out, we were like, hey, let's do that on Earth. So basically the key to nuclear fusion reactors is that they have to be able to confine or trap the plasma such that this reaction can take place. So if we can figure that out at a large scale commercial level, it could be a very good source of clean energy. So I'll get into solar physics now. As I just mentioned, the nuclear fusion process is what converts matter into energy, and it is what's happening in our sun. So I have some numbers here. In a year, the sun produces 44 quadrillion, which is 44 with 16 zeros behind it, watts of power. And our most efficient, our largest power plant produces about 1 billion watts, which is 1 with 9 zeros. So you can see the stark contrast there. So you would need like 44 million of our biggest power plant to produce what the sun does. And in a single second, the sun converts 4 billion kilograms of matter into energy. So it's doing a lot. It's a very active star, and it also has a bunch of different layers that are doing things. So I'll point to this picture here. So you have your nuclear fusion process going on at the core of the sun, and then this energy radiates out in what's called the radiation zone. And then afterwards, there's this convection zone where the plasma sort of moves around. And this movement is what creates the magnetic field of the sun, which I will also describe in a bit. And in this picture, I'm just showing you all the different energies that the sun emits in. So when we use our telescopes, we can look at the sun and all these different energies and basically see all the different layers of the sun. So again, for some more history, these are some pictures I found from the 1800s. But basically, the first one is the first spectrum of the sun. So this was from Fraunhofer, who basically decomposed the sun into its energies, just like I mentioned, but into a spectrum. And this was done in 1817. This is the first daguerreotype of the sun, which is basically this very old school photograph. I don't understand how it works. It's something with like an iodine tablet. I don't know. But yeah, so that's how they made that in 1845. There's Carrington's drawing of a solar flare, 1859. And then this was a solar eclipse in 1860. Raise your hand if you saw a solar eclipse this year. Oh, a lot of us. Okay, so this happened in 1860, and they couldn't take pictures, so they drew it. And that's a nice drawing. So, and then my last one here is a drawing of the solar sunspot cycle, which I'll get into in a little bit, but basically they were noticing that there were these spots on the sun, and there was a cycle to them. Basically, they repeated every 11 years or so. So they were doing a lot of very interesting research back in the 1800s. And that sort of set the tone for what we know now. Okay, so let's go back to what we know about the sun and its magnetic field. So we quickly realized that there was this 11-year cycle of sunspots. So every 11 years, if you can see in this picture here, every 11 years there was a solar maximum. And what a solar maximum is basically the sun being super, super active. There's a lot of sunspots, a lot of flares, and we're actually in a time like that right now. The 2024, 2025 years are basically solar maximum. So that's why we've been seeing a lot of solar activity. If you've seen the aurora borealis this year, that's why. So another very interesting part of this cycle is that the sun's magnetic field, which I will describe what a magnetic field is in just a little bit, its magnetic field basically switches polarity. So what this means is that the north and south side of the bar magnet, or the north and south side of the sun, switch. And this cycle roughly corresponds to the sunspots that we see. So it's actually because of the sunspots that we see. And one last thing I wanted to emphasize is these structures are very, very big compared to the Earth itself. If you see, that's just one sunspot, and that's the size of the Earth. And same thing here. This is another big structure that we see on the sun, and that's the size of the Earth. So these are pretty big structures, and they're very dynamic structures. Okay, so now I will describe what a magnetic field is. Also, I didn't mention this, but if I have something in red, it's because it's a new definition or a new concept. So that's why I'm doing that. Okay, cool. So if you've ever used a fridge magnet, you've probably put the magnet close up to the fridge and notice that there's this like force that happens. And that force, the attraction or the repulsion, is basically due to the movement of charged particles. So this movement of charged particles is basically the magnetic force. So what a magnetic field is it describes how this magnetic force is now distributed in space. So we often represent this with these magnetic field lines. So if you see in this GIF here, this kind of happens naturally when you just pour a bunch of iron filaments onto a bar magnet. You can see the magnetic field lines over here. just with how they rearrange themselves naturally. So when there's a bunch of magnetic field lines bundled up together, then that means that that is a very strong, very magnetic area. Has a very strong magnetic field there. And it also has a strength and a direction. Okay, so now I'll give you some definitions about the sun. The one that I've talked about a lot already is what a sunspot is. So it's basically these very active regions. There's a concentration of magnetic field lines there, so they're very magnetic. And what happens from these sunspots sometimes is a solar flare, which is up here. And it's a very intense local emission of radiation, so it's pretty sudden. Then we also have these things called solar prominences over here, which is this big plasma loop that just sort of arises from the surface. And the corona is this outer layer of the sun. So it extends out into space. And in this layer, we often see coronal mass ejections, which are also called CMEs. And this is basically when a prominence gets crazy and it breaks apart from the sun. And when it breaks away, this expulsion of particles sort of goes out into space. And then these are, again, the zones that I mentioned earlier. We think that the magnetic field of the sun is generated somewhere over here between the radiative and the convective zones because of the motion of plasma. Okay, so as you've probably guessed, the Earth also has a magnetic field. And it also extends out into space, and it looks like this. And it is also generated due to the motion of something, but this time it's not plasma. This time it is molten iron and nickel that's in the outer core. So basically the movement of these currents is what generates our magnetic field. And the Earth's magnetic field is very important for survival. It deflects away charged particles that would otherwise strip away our atmosphere. And we do want to keep our atmosphere, so it's very important that we have it. And I also have a picture of a compass here to remind you that the metal needle of a compass aligns itself with the magnetic field of the Earth. So that's how we know what north is. Okay, so I also wanted to mention more about the Sun-Earth relationship. So in the last slide, when I was talking about solar particles being ejected from the sun and coming towards Earth, what I'm actually talking about is the solar wind. So what happens in the solar wind is there's an outward expansion of plasma from the sun's outermost layer, or the corona. So it kind of comes out like this, and eventually all the objects in our solar system will interact with it. And another definition is what a magnetosphere is. And this is basically the region around a planet where it's dominated by its own magnetic field. So here we have the Earth and its magnetic field. The particles from the solar wind come in from the left here, and they sort of go around and are deflected by Earth's magnetic field. And some of the particles actually reach the Earth just by following the magnetic field lines. So just a little bit more about the solar wind. In the early 1900s, we sort of thought that there might be a solar wind or something like it, mostly because of comet observations where they saw these comets coming in and sort of deviating in their paths, along with space weather, which I'll describe in a little bit. But these are basically the main reasons that they thought there was a solar wind, but early attempts for a theory were unphysical. The math didn't make sense. They didn't really get it. But then this guy named Eugene Parker came around, and he basically solved, ooh, that got loud. He basically solved this problem by saying for the pressure and the density to be realistic at large distances from the sun, the sun's outermost layer must be expanding continuously. So just mathematically, for that to be true, it must be expanding. So there must be a solar wind. So he wrote all his math up and he submitted this for publication. And every single reviewer thought he was crazy. They all said that he should go back and learn physics, doesn't know what he's talking about. But eventually there was a scientist named Chandrasekhar, who's actually pretty famous, who didn't see any flaws in his math and decided to take a chance and let him publish. And then about a decade later, the solar wind was confirmed by Mariner 2, which is a NASA mission. So yeah, he was right. There is a solar wind, and now he has a probe named after him. So take chances. Okay. Okay, so I also have a picture of a bunch of NASA missions here. So there are a lot of instruments out there. Some of them here are studying the Earth's magnetosphere, and some of them are studying the sun a lot more closely. So I'll point out our friend Eugene's solar probe here. So this one actually goes really, really close to the sun. It's actually the closest thing we've sent, or the thing that is closest to the sun that we've sent out. And there's, yeah, a whole suite of instruments. Some of them study the dynamics of the sun's surface. Some of them study how these solar wind particles interact with our magnetic field. Yeah, and I also have another fun fact about the Parker Solar Probe. It's actually currently the fastest object ever built on Earth. It's currently reaching about 0.06% of the speed of light. So yeah, it's zooming and it's very cool, and it's studying the sun in a lot of detail. Something that I thought was interesting was that early on, people were wondering whether this 11-year cycle has anything to do with climate patterns that we see on Earth. So, you know, it like kind of makes sense because it's like, oh yeah, like the sun has a cycle, maybe it affects us on Earth. But that's wrong. So, so in yellow, we have the energy received from the sun, and in red, we have the global temperature of the Earth. So over time, we can see that there's sort of these regular ups and downs in the energy received by the sun, but the temperature on Earth has been increasing by a lot. So yeah, so there was no correlation there, but it was worth looking into. So yeah, global warming is way too large to come from solar activity. And it was basically one of the things that helped scientists realize that climate change and global warming is due to human activity. Okay, so now I'll talk about space weather, which I sort of mentioned earlier. Basically, space weather is known as like the consequences that come about once the solar wind is interacting with the Earth's magnetic field. So there's a whole bunch of things that can happen, and one of them is a geomagnetic storm. So this is basically a large disturbance in Earth's magnetosphere due to the solar wind. And the largest geomagnetic storm in recorded history is called the Carrington event in 1859. And you know, none of us were around then, but it was like a big deal at the time. Oh God. It was a big deal at the time, and there were like telegraph lines on fire. It was very scary. So nowadays we are much more reliant on technology. We have a lot of it. I'll emphasize in this diagram, when solar wind particles come in, they can damage the electronics on our satellites. They interact with the particles in what's called our ionosphere, which is the ionized part of our atmosphere. So here they basically bounce signals, bounce our radio wave signals, bounce signals from satellites. They can also affect aircraft. And because there's now a whole bunch of energized, like there's a whole bunch of electrons now coming towards the Earth, there's actually going to be an induced current in our power system. So that's that could cause fires, that could cause power outages. So with a world that's much more reliant on technology than we were in 1859, it's very important that we monitor solar activity and that we, you know, have safeguards in place for our technologies in case something does happen. Okay, so now I'm sharing pictures that I've taken related to the sun this year. The first one is a picture of the sun. I was like, oh, I heard that there's a solar flare. Maybe there's a sunspot, and there was. You can see it right here. And this middle picture was during the eclipse, which I saw, like many of you. And during the eclipse, we can actually see the corona, which is the outermost layer of the sun. And lastly, here's a picture of the aurora, which I guess I'll go back to the last slide. Yeah, so with interactions in our ionosphere, you can also get these pretty colors because there's also particles in our atmosphere. These new solar wind particles interact with them and make these pretty colors. So yeah, so that was cool. And you could even see this just in or outside of Toronto. So because it's a very active year in our solar cycle, we were able to see these phenomena. Okay, so now I'll introduce sort of the big concept that will pave the way for the rest of the talk. And it is called magnetic reconnection. So you can see it in this GIF here. Basically what happens is magnetic field lines that face in opposite directions come together, they break, and then they reconnect. And because of this, they now go in opposite in this direction. The GIF is better than my arms. So basically, this term was coined by the scientist Dungy, who was studying the solar wind. And there were actually a lot of scientists before him that thought that there was something like this happening with magnetic fields. The key here is that the energy in those magnetic field lines is converted to the energy, to the kinetic and the thermal energy of particles. So what happens is in this reconnection, particles get accelerated. So this was later confirmed by spacecraft like the MMS that NASA has sent out that has observed magnetic reconnection. And the first people to do a really nice mathematical theory for this was Sweet and Parker, the same Parker from before. Okay, so I have a video of a reconnection happening in the sun, basically to show you how a prominence can become a CME. So yeah, so that X is where the reconnection's happening. I also have a video of an actual observation. I don't know if my volume will work on this. Okay. Can I have volume, or is that? It's okay if I can't. All she's saying is that there's magnetic reconnection. Okay, that's okay. Thank you. But basically what she's showing is that this loop, sort of, you see this X shape here, it reconnects and then it comes out. So this is the site of the reconnection now. And now, oh, there you go. You see the X shape and it comes off here. And what they're showing here is that there's, I think, RESI data basically confirmed. Oh God, if you go back here. So these orange spots are showing where there was high temperature, and high temperature basically means that, there's kinetic energy, there's now particles there. So this sort of profile of the temperature shows that there was indeed particle acceleration here, and then it does jet out in those two directions. So yeah. Okay. And one last visualization. This is in the magnetosphere of the Earth, where we also see reconnection happening. And you can see it sort of going towards the poles, and that's where the aurora happens, because these particles are now following the Earth's magnetic field. Okay. Oh, next slide. Okay. So despite how much we know about the sun compared to other astronomical objects, at least, there's still many active research questions that we're trying to solve. The main one is the coronal heating problem. So I guess the best way to explain this is if you imagine yourself by a fire. As you walk away from the fire, do you think it would get cooler or warmer? Cooler, right? Yeah, you would think it would get cooler, but the sort of opposite happens with the sun. Basically, the outermost layer, the corona, is 2 million degrees Fahrenheit, but the layer underneath it, the surface, is 10,000 degrees Fahrenheit. That literally doesn't make sense, but there are a lot of theories about why this is the case, but no confirmed answers yet. And one other question is basically solar wind turbulence. So the wind is coming out, it's very turbulent, it's very chaotic, and it still remains very chaotic, very far out from the sun. And there are disagreements as to what mechanism is giving the solar wind the energy to stay so turbulent for so long. So yeah, that's also being heavily researched at the moment. There are a lot of other unsolved problems, of course, but I'm only dedicated one slide to this, so. Okay, so now I'll talk about astrophysical plasmas. So because we now understand that magnetic reconnection is a thing, we understand that it's leading to these outbursts in the sun, it made sense for people to start thinking about other objects where this could be the case. After all, there are black holes with plasmas around them. Neutron stars are also made of them. So wherever we have a plasma, we have magnetic fields, and we could probably have reconnection. So this is sort of a very active research area right now. It's not totally confirmed whether reconnection's happening in these systems, but that's mostly because these objects are so far away. But it is sort of like the most likely explanation we have for large outbursts and large flares that we see from black holes and from neutron stars and from other objects as well. Yeah, okay. So here's a video of reconnection happening, this time in a black hole jet. Ooh, okay. So yeah, it could happen. There's magnetic fields all around a black hole, so it could happen there as well. So I'll move on now to tools that we use to study plasmas. So we have learned a lot about plasma properties from all the experiments that we do on Earth, such as nuclear fusion. And we've also learned a lot from our theories about the sun and all the different spacecraft that we have sent towards the sun. But the final tool that's been sort of gaining traction recently as our computers get better, and as we start thinking about more complicated problems of things that are much, much further away than the sun, are numerical simulations. So these are basically simulations that use the mathematics of plasma and then, simulate the plasma itself. So here I have a picture of nuclear fusion reactor, some more information about the Parker Solar Probe, which we have learned so much from, and the instruments on it. And here I have a picture of a plasma simulation from a postdoc who works here. So these are all very good tools to learn about plasmas. I'll get into the two sort of main types of plasma simulations that people do. The first is called magnetohydrodynamics, which is a mouthful. So I will say MHD. And what this model does is it basically takes the equations from fluid dynamics, so basically how a fluid behaves, and the equations that describe charged particles and how they behave due to electric and magnetic fields. So it takes these sets of equations and it combines them to model the plasma as a fluid. And this is really good for describing the large scale, very zoomed out picture of what a plasma is doing. And there's this other type of simulation called a particle in cell simulation, or PIC simulation, which solves the equation of motion for the particles themselves and models the plasma as a collection of particles. So what this is really good for is describing the sort of zoomed in small scale behavior of what our particles are doing. So I'll talk a little bit about what I do. So I'm basically studying magnetic reconnection in these astrophysical contexts. So I use a code that combines MHD with general relativity. And we need general relativity because now these are very big astronomical objects. So things are relativistic. And I think specifically about the particle acceleration that occurs at small scales during magnetic reconnection. So here I have a very zoomed in picture of one of the simulations I'm doing. And this is sort of the plasma here. And the key here is to think about the particle acceleration at these small scales and be able to model them well enough so that when we do a zoom out and when we do a big simulation, like the one on the right, which is of a black hole, and it was done by my supervisor and his colleagues. So if we basically zoom out and do a large scale simulation, we're now able to, capture the particle acceleration that happens at small scales while also seeing the big picture of what our black hole is doing. So this is sort of an active research area because we have these two types of simulations and we're limited by the computational power we have. We can't just take a whole system and simulate the entire thing. We can't capture all of those scales. So we have two very good simulation types that are good at capturing different scales. And we need to figure out ways to sort of bridge them and sort of see, be able to see what our system is doing on a big enough scale while also not missing the physics that's happening when you zoom in. Okay. Okay, so I'm going to stop this video. Oh no. Oh no. Okay, so basically what I've been doing is adding these sort of toy or test particles to MHD simulations. And you might be wondering, oh, you said MHD was for large scales. Why are you doing small scales? Good question. I'm doing it because we are trying to bridge the gap between these big scales and these small scales. And one of the ways we can do so is by adding these test particles that sort of show how they respond to the plasma without affecting the plasma themselves. So by doing this, you can see, now I'll play my video. The particle is coming in here in blue, and this plasma is here in orange. So as the particle approaches the plasma, it basically starts to get energized, and you'll see this trajectory now turn purple because it's now gained energy. So it gains energy, it becomes purple, and this is basically saying that through interactions with the plasma, it is now accelerated, and this is all because of magnetic reconnection happening. So you can see this also in this plot of energy versus time, where you can see that with time, the energy of the particle is growing as it interacts with the plasma. So the main research questions here are how much do these particles accelerate, and what are the specific mechanisms for their acceleration, and can we capture this sort of small scale energization when we zoom out into the bigger picture? Yeah, and obviously this can all be related back to the physical systems that I was talking about earlier and how magnetic reconnection leads to particle energization that leads to these crazy outbursts that we see. How can we connect these simulations back to those systems, like the sun, like black holes? There's a lot of applications. Okay, so with that, I'll just say that studying the sun has taught us a lot about plasmas and has taught us a lot about astrophysics, but there are still many, many things to learn from it. So I hope that this helps you see the sun in a new light, but just don't look at the sun for too long. Thank you so much.
All right. Thank you, Tanisha, for a wonderful talk. We have a bit of time to take some questions. So if anybody has any questions, feel free to raise your hand. Yeah.
How big can a solar flare be?
That's a good question. That question is, how big can a solar flare be?
Big? I don't know. I don't know. Definitely hundreds of kilometers, but definitely bigger than, not hundreds, thousands, millions? It definitely can be bigger than the Earth, though. A lot of Earths. I'll say about 4 Earths, at least. Does that help? Not really.
Yeah.
Yeah, that's a good question. The sunspot cycle. Oh, the question was, do we have a theory for the 11-year cycle of the sunspots? Why it's 11 years specifically, we don't understand. But what's happening during that time is basically the sunspots themselves sort of migrate. So they migrate from, let's say they started at the equator and then they migrate towards the poles. And when they do this, that's when the magnetic field poles switch. So the reasoning might just be that the sun is like the right enough size for those sunspots of that size to be moving up. But yeah, it's definitely an active question. Yeah. Yeah.
To jump on that, is there similar cycles in other stars?
Yeah, there are definitely similar cycles of like magnetic fields changing and these structures forming on other stars. We don't know exactly like the timing of them, what structures specifically they have, because we don't see those stars as closely, but yeah, they definitely do have some like spots on them as well. Yeah.
Regarding your research in reconnections on black holes, since those are energetic events, would that be a way to get energy and information out of black holes?
Information, I'm not sure. That goes into a field I don't know much about. But energy, yes. Emissions that we see from black holes, we really do think that magnetic reconnection is, one of the ways that those emissions, those outbursts can happen from the disk around black holes, for example. So, yeah. I don't know which one. Yeah.
When the magnetic field shifts from the sun.
Yeah.
magnetic fields affect so much of what we do on Earth. Is there any information or research on whether these fields shifting could possibly be affecting all the things we do from going into space?
Yeah, that's a good question. And I think it was actually a big question that people had early on. There were studies on whether this shift in polarity actually changes things that we see from the sun. But no, I don't think there was anything that was, catastrophic or that, changes the way we live our lives. And it is important to remember that this flip happens very gradually. So it's very slow over the 11 years or so. So yeah, there's not any real implications of that, but it is something that people have researched. Yeah. Sorry, I couldn't hear the end of it. Yeah. Yeah. Oh God. Okay. So, oh yes, I'll repeat the question. So basically, what are the theories for why the corona is much hotter than the underlying surface? I think the big theory that they have is basically about what's called a dynamo. So it's basically this big movement of plasma. And they think that because of that, the convection currents on basically at the corona are basically generating these outflows that go into the corona instead of, or that go out of the corona instead of stay on the surface. But I'm not really sure how all of that works. I don't think anyone really is, but I think it's the dynamo theory, if you wanted to look it up.
How does the partner solar probe set plasma?
I'll go back to my slide about the solar probe. Okay, so yeah, so it has a whole bunch of instruments on it. I think the main ones are like the magnetometers on it that basically measure the magnetic and electric field at various points. But I think it has a whole bunch of instruments, and what it's trying to do, or it has a very good heat shield on it. So it's like the best heat shield we've ever made. It can withstand the very hot temperatures that are over there. So basically, we want to get it as close to the to the corona of the sun as possible, and be able to study specifically the magnetic loops, like the prominences, the solar flares that erupt from the surface, and why they're erupting. So yeah, I think magnetometers and I want to say magnetometers and like the antenna and stuff, like those are like the most important instruments on it.
Why does magnetic convection occur? I seem like why like what causes magnetic fields to come together?
Yeah, that's a good question. So basically just like as plasmas are moving, so you can think of the magnetic fields lines sort of being attached to the plasmas themselves. So as the plasma is moving, the magnetic field lines are moving with it. So once there's this movement, as things get more turbulent, there are moments where these magnetic field lines can come together. And when they come together, that's sort of when reconnection can happen. Yeah, hopefully that answers your question. Okay, yeah. Uh-huh. Yeah. That's a good question. Yeah, is there a Coriolis effect sort of unique to, you said like a G2 star? I'm not sure. I wouldn't see why it would be unique. But I mean, it depends on the rotation of the star itself. So maybe it would be faster in a star that's rotating faster, or maybe there wouldn't be a Coriolis effect at all. Yeah, that's fair. That's fair. Yeah. Yeah, if there's not enough energy to keep up the convection currents, then maybe there wouldn't be that sort of effect. Yeah. Yeah, I'm not sure. Yeah. Yeah. Yeah, cool. So I basically did an internship in my undergraduate degree where I worked on space weather, which I talked about earlier. Basically, I worked with the government of Canada, and we were looking into how things from the sun could affect technologies that we have here on Earth. So yeah, I was like, whoa, that's cool. I've never thought about the sun in that way. Like I didn't really think it affected my life. So yeah, I sort of did it then. I've done some more computational work since then. And then I sort of realized that I wanted to do simulations, and I like the sun. So it kind of combined eventually. And yeah, that's how I got here. Okay, I don't know, you choose.
Let's take that question.
Are there any plans
Sorry, what was it?
are there any plans to replace the Parker Solar Program?
I don't think there are plans currently. I'm not sure what the mission lifetime is, but I think it's going longer than what they had originally thought. I don't think they're going to be replacing it necessarily, but they're definitely going to be sending more probes out to the sun to study things like that. So yeah, I don't think there's plans to replace it, but I might be wrong.
All right. Thank you so much, everybody.